Lesson 8.4 is on complex and imaginary numbers. In our number system, we've dealt pretty much with real numbers the entire year. And remember, real numbers are broken down to rational and irrational, and then each one of those are broken down into different sections. But now we're going to talk about imaginary numbers. Basically, it's what happens when you arrive at the square root of a negative, right? So our index is 2, and we're taking the root of it. We know that in order to have the square root of something, it needs to be positive. But this happens so much in mathematics that there needed to be a number system that dealt with it. And so when we're talking about imaginary numbers, we are talking about the square root of -1, which equals the sort of cursive letter I. The square root of -1 just represents taking the square root of a negative. So if I had the square root of -4, really I can use my property of radicals and break that down into two parts. The square root of +4 times the square root of -1, which then the square root of +4 is easy, that's 2, and then the square root of -1 is I. And so there's our imaginary number that represents the square root of -4. In this section, we're also going to talk about complex numbers that have both real and imaginary terms. So imagine if I had something like this, 3 plus 5i. This is a complex number because it's got a term that's real and a term that's imaginary. So when we're talking about I as an imaginary number, remember, just I to the first power equals the square root of -1. Well, all of our exponent rules still apply with this. So if I had I squared, that's the same thing as saying the square root of -1 times the square root of -1, which is the same thing as saying -1. Because remember, when you have the square root, let me come up here for a second, when you have the square root of -1 quantities squared, the square and the square root cancel out with each other. So our radical rules also still apply. And we're just left with whatever the radicand is. So I squared is just -1. I cubed would then be I to the second times I to the first. Well, we know I to the second is -1, and I to the first is just the square root of -1. So then that is -I, if we're looking at those two parts. We've got -1 times I, which is just the opposite of I. I to the fourth is going to be I to the third times I to the first. Well, I to the third we've already calculated. It's the opposite of I. And I to the first is just I. So then that would be the opposite of I squared. We know what I squared is. It's -1. So that would be the opposite of -1, which is just 1. So it's kind of fun to play around with these and see what they simplify to. I to the fifth is I to the fourth times I. But we know I to the fourth, that's +1. And then we know I, that's the square root of -1. So we're back at I. Just plain I to the first. And these will repeat. So I to the sixth is the same as I squared. I to the seventh is equal to I to the fourth. I to the eighth is equal to I to the fifth. It's kind of fun to see how these patterns work. And I made a mistake here. I to the seventh is equal to I to the third. I to the eighth is equal to I to the fourth. There we go. Here are some basic examples. Example 1. What if I gave you something like I to the 22nd? Well, we know that this pattern repeats every four exponents. So I to the first, I to the second, I to the third, I to the fourth, and then I to the fifth is the same as I to the first. I to the sixth, I to the seventh, I to the eighth, and so forth. Well, I can just look at this exponent of 22 and figure out how many times does it go through this pattern. So 22 divided by 4 is 5, remainder 2. So it's going to go through this pattern 5 times exactly and have 2 left over. So that means I to the 22nd is the same as I to the second. And remember, I to the second is -1. Example number 2. What if I had the square root of negative 25? Well, the square root of 25 is 5, and the square root of negative 1 is I, so it's 5i. Example 3. What if I had plus or minus the square root of negative 8i? Well, here, again, I can break this down into 2 parts. And so I have plus or minus the square root of 8, which we know is plus or minus 2 square root 2. And then we've got the I component from here. And the way we write this is plus or minus 2I root 2. All together like that. Okay, I'm going to show you the proper way to write ones that are written like this in the next couple of slides. So imaginary numbers are a subset of complex numbers. And complex numbers have 2 parts. They have the imaginary part and the real part. When we're writing complex numbers, order matters. We don't commute complex numbers, so the real term always comes first. The general form for it looks like this: A plus BI, where the real term is always written before the imaginary term. Okay, so A represents the real part, and then BI represents the imaginary part. We can treat these like terms. So if I were to add these together, I have 2 complex numbers here. 8 plus 4i is one number, and then 12 plus 8i is another. But I can add them together by adding their real components with their complex with their imaginary components. So 8 plus 12 is 20, and 4i plus 8i is 12i. And again, I write the real component first and then the imaginary part second. The same thing happens if I'm subtracting, right? I can still distribute. Multiplication properties still apply. So I'll distribute this negative through, and I really have negative 6 plus I is my first complex number, plus negative 3 plus 4i if I distribute that negative all the way through. And that gets me negative 9 plus 5i. And again, the real part is written first. We can also multiply and divide complex numbers. Let's start with multiplying them together. Here I have the complex number 2 plus 3i times 3 minus 2i. And again, I'm just going to distribute, or FOIL, just like we did when we had regular binomials times binomials. So my first gives me a 6. The outsides give me a negative 4i. Insides give me 9i. And then the lasts give me negative 6i squared. Now it's just about simplifying. I have the 6, negative 4i, and 9i are combined to get 5i. And then negative 6 times I squared. This is, you just have to remember that I squared is a value. I squared is the same thing as I times I, or just negative 1. So this really is negative 6 times negative 1, which is positive 6. We continue, and I get 12 plus 5i, and it's now written in its proper form. Go ahead and pause and try the next 2 on your own. Wait a couple seconds, and when you come back, the solutions will be up for you. Okay, here are the solutions to those next 2 examples. Note in this one that the 2 middle terms canceled out. Alright, now let's look over here at the special product patterns. These still work as well. And so here I have 4 minus 3i squared. We treat this just like we would a binomial squared. So we know that that's going to be the first one squared plus 2 times the product of those 2 terms plus the second one squared. So 4 squared is 16. 4 times 3i is negative 12i, and that times 2 is negative 24i. And then negative 3i squared is going to be 9i to the second, positive 9i to the second. We simplify I to the second as negative 1, and then we can simplify these terms. Minus 9, 16 minus 9 is 5, and so I have 5 minus 24i. Okay, and the next one we have a sum and difference pattern. Remember, a sum and difference pattern means One term is the exact same sign, same value. The other term is the same but opposite signs. And here that happens. I have negative 2 plus 5i and then negative 2 minus 5i. Again, this distributes to a difference of two perfect squares. So all I have to do is take negative 2 squared minus 5i squared. And so that's positive 4 minus 25i squared. But remember, the I squared is just negative 1, so that's 4 minus 25 times negative 1, or 4 plus 25, which is 29. Now, true complex numbers have rules for being completely simplified. Well, really only one rule. The real part always comes first and is written in this particular form. But because that's a rule, that means that there are no imaginary parts in the denominator, and we still have to do some rationalization. If you recall, rationalization is the act of getting rid of, well, in our case, radical from the denominator. But we're also going to talk about how to use rationalization to get imaginary numbers out of a denominator and set them up in proper complex number forms. Okay, so let's go through these really quick examples. If we look at A, we have the value of 7. 7 is obviously a real number. If we were going to write this in complex form, the appropriate way to do that would be 7 plus 0i. That gives us a complex component as well as a real component. Remember, 0 times anything is 0. If you're given just 3i, as in example B, and I wanted to write that in complex number system, then it would be 0 plus 3i. Again, we have to put it in proper form, so the 0 will come first. What about C? Well, we can easily evaluate the square root of negative 16 now. So it's 4. We're taking the negative of it, so minus 4i. Both of those have a 4 in common, but realize that this is not complex form, if this is the proper way of writing it. Okay, now let's look at D, negative 5 over I. I can't have the I in the denominator, and I want to make sure that I have it in this form up here. So I'm going to multiply by I. Remember, if I have I squared, that value is just negative 1, right? Or I to the 4th would be the other one. That's just positive 1. These would be the two that we want, because the other two, I cubed and I to the 5th, and then regular I to the 1st, all have the negative radical in it. So we don't want that, right? Remember, I just represents a radical, so it can't be in the denominator. So I'm going to multiply by I to the 1st to get I squared in this denominator. And then I have negative 5i in the numerator. And remember, I squared is just negative 1. So I have negative 5i over negative 1, or just 5i. And if I want to write this imaginary number in complex form, I need to put 0 plus 5i. What about E? It's kind of the same idea. I can't split these apart and just put them in the proper complex form. So I need to multiply by. Do you remember the word? It starts with a C. Conjugate. So I need to multiply by the conjugate here. And I know that by multiplying by the conjugate, this gives me a difference of two squares, so I'm just going to be left with 4 minus I squared. I'll do the same in the numerator, which means I'll have some distribution to do. 3 times 2 is 6. 3 times negative I is negative 3i. Negative I times 2 is negative 2i. And then negative I times negative I is positive I squared. All over, and I have 4 minus I squared down here. Collect my like terms up here, and remember, I squared is just negative 1, so 6 minus 1 is 5, minus 5i over 4 minus a negative 1, or 4 plus 1. So it's 5 minus 5i over 5. And then I can split these apart. 5 over 5 minus negative 5 over 5i, which just leaves me with 1 minus I when I simplify it. Okay, this is the last slide of examples. Go ahead and try these on your own. Wait for a few seconds after you pause, and then pause, wait for a few seconds, and then the solution will pop up for you. And we can discuss these more in class. Notice in this first example that we leave those as two separate terms and as fractions. And notice in this example we added in our imaginary term.